Hello guys, good morning. Welcome to our channel where we usually share basic principle of any engineering system. So today our topic is about communication technique, which I make it short as amplitude modulation. Before I go further, I would like to make a scenario. Okay, so imagine yourself living in Johor Bahru, and now you are trying to send your voice to someone that is located 200 kilometers away. For example, is at Pulau Pinang. So without the use of technology, the act of transferring your voice to someone located 200 kilometers away is something illogical, something impossible. So by using the communication technique, which is amplitude modulation, which can be divided into full carrier and suppressed carrier, we can make it possible to transfer our voice to someone located 200 kilometers away. Without further ado, let's go into this slide to see more on how amplitude modulation is all about. Okay, the first thing here you can see is message signal. So try to imagine that this is our voice, and another one is carrier wave. So carrier wave is actually a wave that we increase the frequency higher than our original voice. Okay, so by combining these two input, we can get amplitude modulation wave, which basically look like this red line here. The reason why we produce amplitude modulation wave is that we want to increase the power and energy contained by the wave itself, so that it can travel far away. As someone need to know, modulation index is quite important, as it can affect the quality of the voice that we transfer. The ideal modulation percentage is between 100% and also 50%. If I change this into modulating index value, 50% means 0.5 and 100% means 1.0. And to obtain the value of modulating index, we're using EM over EC. So what is EM? EM is the amplitude of original signal, our voice, and also EC is the amplitude of carrier signal, which has a high frequency. Okay, so by using this simple formula, we could obtain the modulating index value. Alright, so what if the modulating index value is bigger than 1.0? Okay, so as you can see here, 150% modulation, we could see a small part from negative 0.5 to 0.5 as a distortion. This small part as a distortion, a part that we should consider as not good for the system, because at this small area we have lost some of the information that we are actually trying to convey to people that is located somewhere around the world. So as for me, I choose MATLAB application to simulate how amplitude modulation is. Alright, so as you can see here, I divide it into amplitude modulation full sideband, and another one is amplitude modulation suppressed carrier. Okay, so as I run this program, okay, I will obtain a graph that pretty much look like this. Okay, so this is message signal this one is carrier signal, and lastly is amplitude modulated signal. So for this case, okay, so in this program, the best part is I can show all the effect of modulating index value. So if EM is equal to EC, that means we're gonna get a graph that look like this. Okay, but I have to change the coding. So by this coding, it's just that I have to change the value of EC in order to simulate the amplitude modulation that been modulated as much as 50%, 100%, or even 150%. Okay, so let's see. Now I'm going to change the coding so that I could get amplitude modulation signal that is 50% modulated. So if I'm changing the value of EC to be big value, okay, in other words, the amplitude of carrier to be big value, I could obtain a small value of modulating index. Alright, so I can show you guys and I can simulate the 50% modulating procedure. So this is how it looks like when I'm changing the value of EC to be big. Alright, so this is how is it. Now I'm showing you guys what if I change the value of EC to be small. Okay, let's say I divide it by maybe I divide it by 10. Okay, I divide it by 10. Oh no, yeah, I divide it by 10. So now my EC is small, and when EC is small, divide it by message signal amplitude, I will get something big. Okay, where this is how I show you and how I simulate the 150% modulating signal. So next is double sideband suppressed carrier. In this part, okay, it almost the same as full carrier. It's just that in the frequency spectrum, we does not consider the carrier frequency part, meaning that we only take the upper sideband and also the lower sideband to be transmitted in the transmission channel. Okay, so after I run the program, the coding, this is how I get for the signal, right? So this is my message signal. Still there is a carrier signal, and in time domain representation it almost the same as full carrier. It's just that there is a difference when we see in frequency spectrum, where we omit the frequency carrier part. So by looking at my slide that I provide here, I make a clear distinction of frequency spectrum of full carrier and also the frequency spectrum of suppressed carrier, where now you can see there is no amplitude taken for the frequency at the carrier frequency. Only consider the upper sideband as well as the lower sideband. Okay, so other than using the coding, MATLAB also provide me tools to simulate how to get full carrier with modulation index of 1 or 0.5 or even 1.5. Okay, so I use Simulink. Okay, I use Simulink and I connect the block here, as you can see, and then I put different gain. So if I want the ideal case 1, so I put the gain is equivalent to the amplitude of massive signal. So if I want 0.5 modulation index, so I put 5 is divided by 10. Alright, so let's see what happens if I change the gain to be 10. Alright, so apply and see by clicking at the scope here. So okay, before that I have to save it and then run it. Okay, and then put at the scope. Alright, so click the auto scale and we're gonna get the output result of the modulating signal. So this is for the case of M1. Okay, now I'm changing the value of the gain to be 3.3. Okay, so why I choose this value? It is because 3.3 will possibly give the output modulation as much as 150%. For double sideband suppressed carrier, this is how the block diagram looks like. We have massive signal and we have carrier signal. So where the gain is we kept constant as 1. Then combine it using the product and then put it to the scope so that we can see how the wave looks like in time domain. By running the block diagram, by running the system, I could show you how it looks like. Okay, so this is how double sideband suppressed carrier modulating signal looks like. Okay, so with that, I'm going into the application of amplitude modulation in real world.
Okay, now we continue with the application of amplitude modulation. Basically, amplitude modulation is widely used in broadcasting and also in electronic communication. This is because basically it is simple to demodulate, and this means that radio receivers capable of demodulating amplitude modulation are cheap and simple to manufacture. Next, as amplitude modulation has lower frequency, hence it is widely used in aviation and navy because it can transmit signal across larger distance.